in this example, we have these four forces that are acting on this wheel, and this wheel has a 10-centimeter radius. Now, there's nothing that guarantees this, but in this problem, we're just deciding that the axis is at the center. Okay, the axis could be anywhere. It could be on the side, on the top, on the bottom, on the far right. It could be not even on the object, it could be somewhere in the middle. These are these examples where torque would be different. And so each one of these forces will exert a torque about this axis. These forces will exert different torques about different axes, but we're not doing those. So let's do the example of at the center. So the first one, so okay, but for a labeling perspective, let me just label the first one F1, the one at the top, and then the one on the upper left is F2, and then F3, and then so on. And then F4 is this one at the bottom here. I'm going to calculate torque in the way that I would recommend folks calculate torque when they're first learning this. And that is, you draw the picture as many times as you need to. Even from my experience, just looking at this picture, it's really hard to calculate the torques just by looking at this picture, because you got lots of arrows already, and you typically need to draw more arrows to get a feeling about the torque. And so there's nothing wrong with just drawing the vectors in their own little section. So I'm going to calculate tau 1. That's Greek letter tau, by the way. Let's do F1. So the R vector starts from the axis to the location of the force. So the vector R1 will more or less point straight up. Okay. After that, we would draw the force we would draw the force in its direction at its location, which is right here. But again, that makes it kind of hard to visualize the angle. So I'm going to bring the force down to the origin, or the axis. And so that way the tails of these two vectors line up. And when you line them up like that, you're more clearly able to see the angle. And you might think to yourself, well, the angle is just 90. But the angle, the phi in the definition of torque, is defined as the angle from R to F. And with our typical convention, that's going to make phi1 a minus 90 degrees. So phi1 has an angle of minus 90 degrees. Doesn't really look like they're 90 degrees, but now we can calculate it. So I'll calculate it below right here. So we have tau 1 equals, I need to split it up into two lines. So 0.1 meters, magnitude of R, times 30 newtons, the magnitude of F, times sine of minus 90 degrees, sine of the phi. And so the sine of 90 is minus 1, 30 times 0.1 is just swapping the factors of 10. And so you get a magnitude of minus 3.0. Units of torque, as you probably had seen, are Newton meters. That might make you think that it's the same as work and energy. Certainly the units are the same, but this is an example where the presence of angles kind of can cloud our interpretation. Why does torque have the same units as work? Torques can do work just like forces, but it's a little bit different, right? On the upper right-hand side here, the classic picture of a force, acting on an object as it goes a displacement, delta x, right? The work done by that force is when it acts on the object over that linear displacement, and therefore has a change in kinetic energy. So that has newtons per meter, but torques don't do work over displacements. Torques do work over angles. So that same force, if it pushes along the wheel over this change in angle, then that force, and usually we assume the force is kind of like tangent, always tangent to the circle. The work done by the torque would be the magnitude of the torque times the change in angle. That's where how torque and work are related. The book doesn't really focus on an equation like this, but certainly that torque can change the rotational energy of the object as well. So that's why the Newton meters are there. Returning to our problem though, another remark to make about torque is that this is only the magnitude. Technically, torque is defined, like I said, as a cross product, R cross F, up at the top left here. So if it's a vector, then what's its direction? And that answer has to do with the right-hand rule. So if you take your, in this case, if you take your thumb, so the right-hand rule tells you that if you take your thumb in the direction of the first vector and your index in the direction of the second vector in the cross product, the middle finger will always be the direction of the cross product. So in this case, if you take your thumb, point it up, and you take your right finger, point it right, the middle finger points into the screen. So that means that the torque vector for this top force points on the axis into the screen, into the page, into the board, and it's got a magnitude of 3 Newton meters. And so we can even, in this answer, we can even put in the parentheses and give it a K hat because it points in the negative Z direction. You know, if you take your right thumb on this XY plane, you point your right thumb to the right and your right index finger up. Your right thumb is like the x-axis, the right index is like the y-axis, and so the z-axis points out at you. So in this coordinate system, the z-axis always points up, away from the paper or away from the screen. So the negative points into the screen or into the paper. So that's how you calculate tau 1 and some other remarks on it. Okay, so the best way to do this, write the vectors out to recognize the role of the equation the angle plays. So let's try tau 2 next. Draw the vector as usual. So the vector then, it's going to be an R2 that points to the right. And again, the location of the force would be at the point of the position vector. So I'm going to draw that, going to align they're going to be coaxial, not coaxial, but have the same starting spot. So F2 looks like that. And so this angle, V2, is plus 135. You see in the figure that the 45, if you use 45 in this calculation, you will still get the right answer, but that's not always the case. If 45, if the angle might have been like say 45 down here, then you would get the wrong answer. I just drew a white line left to the left, down and to the left of the axis there. Okay, so it's plus 135 here. And so calculating this torque, we have 0.050 meters for the R times the same 30 newtons, now times sine of plus 135 degrees. So now we have a sine of plus 135 degrees, 30 times 0.05, that's like 30 divided by 20, which is 1.5. Sine of 135 is just like sine of 45, it's radical 2 over 2. And so all that adds up to plus 1.065 Newton meters. And again, I would even write it with the K hat, just to know that it is that torque vector from the diagonal force points outward about that axis. This is really one of our first chances to visualizing these problems three-dimensionally. And it's very helpful, especially when you get to physics 2, of calculating these things and thinking about them three-dimensionally, because you have to think three-dimensionally to understand a lot of the stuff from physics 2, and also in some later chapters. So moving on to the upper right-hand part, tau 3. The first two were kind of straightforward, or first two we were figuring it out, so this third one should be kind of straightforward. The R vector now points to the left. That's R3. And so it's going to, so since the F points down, again, lining them up. Now that, so the R swings down counterclockwise or clockwise, counterclockwise into the torque. So since it's clockwise, we still have phi3 equals minus 90 degrees, or minus pi over 2. And you can start to get the hang of this when you do it. So tau 3 is going to equal, 0.05 meters times, now it's 20 newtons times sine of minus 90. And so 20 divided by 20 is 1. And so the vector tau 3, I'll write it again in vector form. It's minus 1.0 Newton meters in the k direction. Sometimes the book uses parentheses to separate the numerical value from the unit vector, but it's all the same. And then finally, I can just draw it on the white of the screen of the picture here, just to verify that what our intuition might have been telling us. This R4, it literally is drawn like this. So I've drawn vector R4 on the wheel. Again, these two are very nearly perpendicular, or parallel, excuse me. So the angle that they make with one another is 0. So we got R4 and then F4. So the angle they make is 0. So as you would expect, the torque exerted by F4 is 0. Or more precisely, it's the 0 vector. And so those are 3 different examples of when we would calculate a torque. All 4 forces exerted different torques about the center of this axis, or about the axis through the center of this wheel. A couple of comments are that the torques might change if you change the axis. If you let this thing go on its own, then it'll just kind of spin like a CD or a record player or a hard disk would. It'll spin around its center, or a merry-go-round or whatever, meant to spin around its center. But that's not the only way that it can rotate. When we talked about moment of inertia means that an object can rotate around any axis, and every possible axis might give you a different moment of inertia. If, for instance, we were to choose, say, the bottom part of the wheel as a potential axis, then you might imagine that the whole circle moves to the bottom and then back around. All those forces will exert different torques because you have to do different calculations on them. For instance, F1, the torque that F1 exerts around the center, we calculated was minus 3 Newton meters. Around the bottom, though, the force that it exerts will be the torque that it exerts will be minus 6 Newton meters. And same thing for F3 and F4. For reasons that are a little more geometric, it turns out that F2 exerts the same torque around that bottom axis. And if you're curious as to why, I would invite you to work it out on your own. You'll see a very, very peculiar, interesting result about the geometry of the cross product, but I won't go into detail in that here. So that's the calculation. Again, where do these torque vectors live? They all live along the axis of rotation. Right? The torque from the first one is points into the screen. Torque from the second points out. Torque for the third points into the screen, all along the axis. And so if we were to draw kind of like a bird's eye view of this axis with kind of the wheel at the top here, so we're looking at top of the wheel. So we're looking at the top of the wheel, and we see that F1 force at the very top. Then the axis of rotation, goes like this, something like that. This is the z-axis. So we're looking at really the xz plane, I guess that's what we're doing. And so if we're looking at the xz plane, then you have vector tau 1, point like that. Vector tau 2 points like this. And tau 3 also points up, or in the negative z-axis. So that's where those vectors live. Again, this is looking from the very top of this picture. That's where the torque vectors are, because the z-axis is the axis of rotation. And so just like any other vectors, we can add them together. It's pretty simple because they're all in the same direction. So you can just add them like normal scalars that are real, that can possibly be negative. And so the net torque on this wheel, if I go on the left side, will be tau 1, which would be minus 3.0 Newton meters plus 1.065 Newton meters for tau 2, and then minus 1.0 Newton meters for tau 3. And this is, kind of the hybrid sort of picture way of adding all these things together. But the simplest way that I would add this is I would take the 3 and the 1, that makes -4, and then take away 1, so that's 3, take away 0.06, that's 94, take away 0.005, that makes it 93.5. So sure enough, we left with a net torque. Let me write that a little bit nicer. We're left with a net torque of minus 2.935 Newton meters. Let me give myself more space. Minus 2.935 Newton meters in the k-hat direction. So all of those 3 torque vectors, again, the tau 4 was 0, so that didn't contribute. All those tau vectors, all those torque vectors, they added up to one that, as you could kind of see, points in the negative z direction. So if I erase those, oops, I accidentally erased my axis too, but there we go. So the net torque then points towards the negative z. Oh, I see. I have a squiggly tau that stuck around. So that's the direction of net torque. Oh, I guess I could just use it. Tau net. There we go. So all of these forces produce a net torque that points into the screen along the axis of rotation. Now, what does that mean? If you take your right thumb, and you point it in the direction of the net torque, then your fingers tell you the direction that the thing will start to rotate if it's from rest. Right, so all these forces, if the wheel's at rest at time t equals 0, all these forces will make the wheel start to rotate clockwise. And after it starts to rotate clockwise, who knows? Maybe those forces will change direction. Typically, when we exert torques in like the laboratory or something like that, it's usually the result of some string that's wound about the circle. The torques generally are, most common torques are generally horizontal or tangent to the rotating object. So like if you were to wind up a wheel, right? If you were to wind up a wheel with a bunch of string and then pull on it, if you pull on it down, the more you pull on it, the more the string will unfurl, but that's still a constant tension, that the constant tension exerting a torque on this rotating wheel, the rotating disc or whatever. So the forces are usually tangent and usually stay tangent to the circle. So this is a good example of calculating torque in different contexts, different practice, and also with the vector notation.